Alright, friends, this is our last lesson on the music of Greece. So, before me and Costa wrapped up our conversation, we brought up this point. Let me zoom it up.
Based on what you're saying, I think he was able to find like ratios of the
Yes,
string. So
ratios,
and
that's the
like
word.
and like the tension, how much the string is pulled to create what frequency. So like these strings, um, we have tuners here, and what this does is it locks the string at a certain tension. It's like when you pull a rubber band and the rubber band gets thinner, and if you flick the rubber band, it's kind of like a guitar string. So what he was able to do was I think he was taking string, and he was locking them on one end of a table and letting the string go across the table and off the edge.
Hmm.
And off the edge, he would put a weight, a rock maybe, like at a certain, had a certain weight at the end of the string around the corner, and then he would put different weights and tensions on the string and
To
produce different notes
oh,
and
cool.
ratios. So what he figured out was like the what we call.
So, before I keep playing what Costa is saying, who are we talking about? We're talking about he. Who me and Costa were talking about was Pythagoras. Here's a quick catch up on.
Three Greek philosopher edition. Today we're going to learn about three philosophers: Pythagoras, Plato, Aristotle. Pythagoras was a philosopher who believed that the universe was organized in a series of patterns. He performed experiments to discover just what these patterns are. He used strings fixed at 2 points, like a guitar string, and discovered that by playing them at certain points, intervals were created. He considered the fourth, the fifth, and the octave to be perfect intervals.
Interesting. Those are the intervals we started with, and the same intervals that medieval churches found to be perfect as well. Let's bring it back to Costa.
Call like the fourth and the fifth, for instance. Um, these intervals and the octave, which is if you look at the bouzouki, this note here is right in the middle of the string. From this point to here is going to be the same as here to the end of the instrument. So this is exactly like halfway of the string.
So the octave's in the middle, which is, if we pull up our scale, is an octave is, if you start on one note, the octave is 8 notes up. The fourth is the fourth note of the scale, so, and the fifth is the fifth note. So here, the first, the fifth, in an octave. Let's bring back this. So Pythagoras had a whole theory based on his intervals and his ratios
from a
he
tomb
found.
in Aden, Turkey. Pythagoras considered that the basis of musical tuning was the relative sizes of the planets. This was called the harmony of the spheres. This consisted in stretching a single string in the proportions 4:1, 3:1, 3:2, etc. This means if a string is divided in a half, you will get an octave higher from the fundamental tone. 4:1, 2 octaves, an octave plus a fifth, 3:1, and fifth and fourth, 3:2, 4:3 respectively. Although this theory was dismissed by the Copernican revolution of the 16th century because of the Pythagorean comma, all these scholars showed how we humans started.
So it didn't predict the planets, but it did help mathematically find how we tune and hear music now. I know this is a lot. Let's check this out. So when Costa was saying the octave on his bouzouki, it's the same with the guitar.
Octave is a 2-to-1 ratio, which means if I was to take a string of a certain length, and I was to find the place on the string that one side was 2 times the length of the other side, the result would be an octave. Well, these ratios don't just work for octaves. Every interval can be broken down using mathematical ratios, which means that we can use ratios to find any interval. And I mean any.
So, I mean, this is some pretty detailed stuff, friends. We don't really need to know all the math to know how to play music, but I find it pretty interesting. And this video shows us how that music looks, and when we combine different ratios of different notes, they have different frequencies. And if you take those different frequencies and play them together, they make sounds that are pleasant and sounds that aren't pleasant. So our sharps and flats mathematically do this. We're going to wrap up the lesson with this. I know that was a pretty heady, complicated look at some of the stuff, but I thought it was pretty interesting and a good way to wrap up not only how the music of Greece sounds and how we find it in pop music like Billie Eilish, but how mathematically it's how we've always looked at music. Alright, so let's check this video out.
It may sound like a paradox or some cruel joke, but whatever it is, it's true. Beethoven, the composer of some of the most celebrated music in history, spent most of his career going deaf. So how was he still able to create such intricate and moving compositions? The answer lies in the patterns hidden beneath the beautiful sounds. Let's take a look at the famous Moonlight Sonata, which opens with a slow, steady stream of notes grouped into triplets. 1 and 2 and 3 and But though they sound deceptively simple, each triplet contains an elegant melodic structure, revealing the fascinating relationship between music and math. Beethoven once said, "I always have a picture in my mind when composing, and follow its lines." Similarly, we can picture a standard piano octave consisting of 13 keys, each separated by a half step. A standard major or minor scale uses 8 of these keys, with 5 whole step intervals and 2 half step ones. And the first half of measure 50, for example, consists of 3 notes in D major, separated by intervals called thirds that skip over the next note in the scale. By stacking the scale's first, third, and fifth notes, D, F sharp, and A, we get a harmonic pattern known as a triad. But these aren't just arbitrary magic numbers. Rather, they represent the mathematical relationship between the pitch frequencies of different notes, which form a geometric series. If we begin with the note A3 at 220 Hz, the series can be expressed with this equation, where n corresponds to successive notes on the keyboard. The D major triplet from the Moonlight Sonata uses n values 5, 9, and 12. And by plugging these into the function, we can graph the sine wave for each note, allowing us to see the patterns that Beethoven could not hear. When all 3 of the sine waves are graphed, they intersect at their starting point of 0, 0, and again at 0, 0.042. Within this span, the D goes through 2 full cycles, F sharp through 2.5, and A goes through 3. This pattern is known as consonance, which sounds naturally pleasant to our ears. But perhaps equally captivating is Beethoven's use of dissonance. Take a look at measures 52 through 54, which feature triplets containing the notes B and C. As their sign graphs show, the waves are largely out of sync, matching up rarely, if at all. And it is by contrasting this dissonance with the consonants of the D major triad in the preceding measures that Beethoven adds the unquantifiable elements of emotion and creativity to the certainty of mathematics, creating what Hector Berlioz described as one of those poems that human language does not know how to qualify. So although we can investigate the underlying mathematical patterns of musical pieces, it is yet to be discovered why certain sequences of these patterns strike the hearts of listeners in certain ways. And Beethoven's true genius lay not only in his ability to see the patterns without hearing the music, but to feel their effect. As James Sylvester wrote, "May not music be described as the mathematics of the sense, mathematics as music of the reason? The musician feels mathematics, The mathematician thinks music, music the dream, mathematics the working life.
Alright, friends, so the music of Greece had a profound effect on the music we hear, and the music we make, and the music that we have now.